let's unpack what's called the reflected resistance in a transformer circuit. Yeah, it's a pretty cool concept actually. It's kind of like, hey, what's the resistance that the source sees through the transformer? Look, here's my question here. Okay, here's the source, and then there's the load. Does the source know that that load is 10 ohms? Like, I mean, really basic example. Just like, let's throw a DC circuit on here. Even actually an AC circuit we can do that with. Okay, so I'm going to do an AC circuit. So I'm doing this guy, a real basic simple circuit here. This is my VS, and let's say that's 10 ohms. Okay, so I have a resistor there, 10 ohms. This guy sees that. The current that's coming out of here, you know, it goes both ways. The current that comes out of here goes directly through here. The voltage that's pushing the current is actually fighting this resistor specifically. So as far as, like, if you were to go over to this thing, it knows what its voltage is, and it knows what the current's coming out of it. So it can calculate, you know, the resistance pretty easily. So if you said, hey, you know, power source, what's the resistance of that load you're driving right now? And it'd be like, you know, it kind of feels like 10 ohms. Okay, so with that concept, oh, where's my eraser? What we're going to do is we're going to ask this guy, what's the resistance over there? So again, kind of going back to what I was saying here, if you were to say to that that source, hey, you know, what's the current coming out of you and what's that energy, what's that push that you're pushing with? Or more specifically, what's the voltage? It knows its voltage, it knows the current going out of it, so it can then calculate the resistance of the load. But can it? Actually, no. Because the current that's coming out of it isn't going through the load. The voltage, the actual energy itself that's being used to push out here, it is not directly seeing this, because that voltage is being changed into another voltage, another value of voltage. So the voltage over here could be 10, and if it's a 1 to 10, the voltage over here is 100. So the current through here is completely different from the current over here. So let's just start kind of looking and unpacking this with N. Yeah, our ratio, our turns ratio. Now, we know that the N here, so we can say N equals 10. Okay, we know that, but that's the turns ratio. Okay, well, we know the turns ratio. Now, let's unpack how the voltage and the current are affected by this N. And then we'll unpack how the resistive load, or how the resistance is affected by N. Okay, so, and then we'll jump into Ohm's law to do that. So right now I'm just going to write these two things down, which we know that N equals, this is from the lecture notes, N equals V secondary over V primary. Okay, that's fine. Now, we also know that N equals I primary over I secondary. Okay, that's fine. So if we know that, how do we fit resistance in here? Well, guess what? This sees a resistance. What resistance does it see? Well, it's kind of the resistance of this whole thing here. The resistance of what's happening in here. So it does see some resistance. How do we calculate what that resistance is, and what do we call it? Actually, we call that resistance the primary resistance. So over here, I'm just going to make a note about that, and I'll do the same over here. Okay, so we know that the resistance primary equals, I might as well use Ohm's law to solve this. In this case, I'm going to say it's the voltage of the primary over the current of the primary. Okay, I think that makes sense. And with the same convention, we can do the same for this. We can say, hey, what's the resistance of this? And by the way, we know its resistance. But let's just go and continue to write it down here. Okay, so we can say the resistance of the secondary is, let me write this, primary is equal to the voltage of the secondary divided by the current in the secondary. Okay, now we happen to actually know that, but that's not where I'm going. I'm trying to actually figure out what N is. Okay, I'm going to take these two and I'm going to say, this guy and this guy, if I just kind of rearrange those in kind of a different way, I can maybe kind of get N out of there, or more specifically, I'm going to get N squared. I'm going to continue with the convention that I have over here. If I can extrapolate what N is by putting the voltage over the voltage and the current over the current, Can I also do that by putting the resistance over the resistance? Actually, yeah, we can. But we don't actually know exactly how to say that. But what I'm going to say is this. If I'm going to say R primary or R secondary, I can do one or the other. Let me actually just start with secondary, because I'm kind of going with this. This is the one that we actually use the most. That's really the most important one. So I'm going to continue that convention, and I'm going to say if R secondary over R primary equals N, can I just write N there? Well, you know what? I'm going to use Ohm's law, and I'm going to write a value of N over here that I know. Okay, just bear with me. This is actually pretty cool. So what I'm going to do is I'm going to say, this R primary and R secondary actually equals this. So I'm going to write these values like this. Over here, I'm going to write this ratio. R secondary over here, that's actually V secondary over I secondary. And over here, I can write V primary over I primary. Okay, so I know that if I'm going to divide this by this, I can just invert and multiply. Okay, so I'm going to go down here and continue this idea where I'm going to say V secondary over I secondary times I primary over V primary. Okay, so now I know that that equals this. Okay, so I'm just going to continue with this. R secondary over R primary equals all of this. And we're fine with that. I think we're kind of getting somewhere with that. Now, oh, wait a second. You know what? I can maybe do some flipping around with some of this stuff and kind of go back to maybe here. Look at this. V secondary over V primary equals N. Is there a V secondary? Oh, look at that. I can rewrite this. Let's do that. Okay, I'm going to write V secondary over V primary times, times, I can do the same thing over here. I don't need brackets, over I primary over I secondary. Okay, so what does that mean? V secondary over V primary. V secondary over primary equals N. Oh, that equals N. Okay, wait a second. I primary over I secondary. Oh, it's N times N. Yeah, N squared. I can say R secondary over R primary equals N squared. Because we know this is N, and we know that's N, so N times N is N squared. So it's pretty cool. So what we can do is we can write this over here. We can also say that N squared equals R secondary over R primary. So we have the three different types of N relative to resistance, current, and voltage. And then from there we can do some really cool math. So I'm going to show you this and demonstrate this in more of a kind of a tangible example. So what's going on here is that why does this, if you were to ask this, what's the resistance? And it would say, oh, well, it's kind of some value over here. I'm feeling that it's some value. And then I wanted to calculate what this was. If you could ask this, what resistance it felt, it could actually tell you this through this formula. So let's actually solve that. It's pretty simple. What I'm going to do is I'm going to rearrange my formula to solve for this. Okay, so I want to know my R primary, and that equals my R secondary over N squared. Okay, so my R secondary in this case is 10 ohms divided by N squared. N is 10, so that's 100. Okay, so that's 0, well, let me just do this. I can say, no, it's 100 ohms. I just started to write it amp. Milliohms. So what's going on here is that if you were to ask this thing, just like we asked that circuit originally, hey, what's the resistance of the load? It would be like, well, I have to do the math. Just hold on a second. Okay, and then it does the math. It's going, well, I'm feeling that the resistance that I am getting here is this much. But because I know the math, I can actually tell you the load over here as well. So that's what's going on. So it's not just clean and simple and clear because we got this n squared, but now that kind of we know the math, it's pretty simple. Now, let's take a look at this really cool example where we can get a tangible understanding of kind of why this sees a different resistance than it's actually dealing with. It's kind of like a lever. Watch this. Alright, so I thought I'd have a little fun with this and set up a little kind of like, I don't know, a balancing act going on. Yeah, so we're going to talk about levers. Now, let's just take a look at that formula on the board. Now, you see that guy? You remember that from like, I don't know, grade 11 physics or something? Yeah, what's going on is that if I knew the mass or the force, which on Earth is the same, actually anywhere, as long as you've got some kind of gravity, that formula is going to work out with mass as well as force. So here we go. I'm going to put mass on the left. So I got ma, and then I got mb. So, and then there's the fulcrum in the middle. Now the distance large A and the distance large B, I have a formula that looks like this. So if I wanted to calculate the mass of B or the mass of A, and I knew A and B or vice versa or whatever, if I had if I had three of any of those, I could calculate A. So, I mean M, I could calculate the fourth. Okay, let's go on. So what's going on here is let's take a look at these formulas over here. I thought I'd kind of have fun with this. Again, yes, we are studying reflected resistance. So you know, look at that formula right there. Okay, so we've got R secondary over I primary equals N squared. We know that. But what's the N? Like, what am I doing here? Like, I'm demonstrating the fact that I've got a different weight over here and a different weight over there, and they're balanced out. So if I'm going to try and compare this to my same reflected resistance, we can see that if I were to say, find some attribute of this side and compare it to the attribute of that side, would some other element be squared in there? And what's that all about? So if I go with just that formula over there, we see that there are no squares. So if I were to say, what's the comparative of resistance in here? Is it the weight of this? Is it the weight of that? Actually, get this. It's the distance that this has to travel. That's really cool. Over the same amount of time. So watch this. This is actually fun. I kind of had fun with this. See this formula? We know that the delta EA is the same as the delta EB. So if I were to move this up and down, okay, let's say this is my A and that's my B. If I were to move this up and down, we know that the kinetic energy is going to be the same because we know that the gravitational potential energy is the same. So if this goes from there to there, and this goes from there to there, I'm doing just as much work on either side. So actually, this thing, although it weighs less, is going farther than that thing. And that thing is going less and it weighs more. So, okay, that's fine. You guys get that. So I can say that the delta E between here, the amount of potential energy here is the same as the amount of potential energy there. But I can also go into a dynamic state where I could see the kinetic energy on either side is the same as well. So during this moment, from here to there, or from here to there, the amount of the same kinetic energy exists over there. So we know kinetic energy is relative to the square of the velocity. So if we take the two and we say, okay, so we know that mass is velocity, energy is mass times velocity. If we take a look at that formula, and we can say E is 1/2 mv squared. Okay, so I can also say that delta EA equals delta EB. So if I boil it down to it, and I get rid of that 1/2, I can make them equal to each other just by saying MA V squared A equals MB V squared B. So if I dial it down a little bit more and unpack it, and I get rid of my T's on either side, so I'm taking my velocity and I'm turning it into distance over time, okay, that's fine. Oh, look at that. I can unpack that more and then I can solve for D, and I'm getting D, so the distance that this travels, this is A, the distance that this travels over the distance that that travels squared is equivalent to the weight of this, the weight of that over the weight of this. So if you're looking for a correlation between physical properties of things that actually go on, in Newtonian physics, and then we also look at electronics, And we can see that kind of Newtonian physics is going on in electronics as well. Especially here, I mean, Faraday was really dealing with Newtonian type physics. I mean, he's, you know, if you go outside of quantum physics, you're dealing with Newtonian physics. So it's kind of interesting to note that there are parallels between physics and electricity. Yeah, and we will also find parallels between electricity, voltage and current and resistance in pneumatics and hydraulics. It's fascinating. So there you go. I thought maybe that you would get maybe a visual of understanding reflected resistance. So pretending, okay, that this system here is a transformer, and I have a certain amount of action going in here, which is a distance that I have to travel. If I wanted to know the distance over there, I could calculate it with that if I knew the weights, knowing that the energy is the same as I'm moving them. So in dynamic, because AC does this, it's just dynamic, if I wanted to understand what was going on, I could unpack it in a physical sense as well. So transformers are actual physical transferring of electricity, because there's a magnetic field that's changing. An electromagnetic field, it's a physical thing. Cool, eh?